Okay, everyone, welcome back. So today we're going to continue with Chapter 5. Last time I went through this material on adders, looked at ripple, carry, carry-lookahead, and prefix adders. Ripple carry, of course, is the slowest. Ripple's the carry through each of the full adders. And so the propagation delay is n, which is the number of bits for the adder. So if 32, 64-bit adder, n would be 32 or 64, and t is the propagation delay of a full adder. The carry-lookahead adder decomposes the adder into groups, in this case 4-bit groups. And it generates a propagate and generate signal for each bit, as well as for each group of bits. Okay, make sense? So propagate means that if the propagate and generate's associated with each column or each bit, mean that propagate is if you have a carry in, then you will carry out. And generate is that you'll carry out regardless of the carry in. So you generate a propagate and generate for each of the columns, each of the bits, each of the individual bits. And the nice thing about that is there's only a 1 gate delay for generating a P and a G. But then you can also generate P and G for each group of 4 bits by going through, taking the individual P's and G's and going through a two-level logic circuit, as shown up here. So the generate for bits 3 down to 0 is the generate of the most significant bit, or the propagate of the most significant bit, and the generate of bit 2, the second to most significant, or the propagate of bit 3 and the propagate of bit 2 and the generate of bit 1, or the propagate of bit 3, the propagate of bit 2, propagate of bit 1, and the generate of bit 0. Does it make sense? So what I'm doing here is I'm distributing, I'm taking this expression and I'm expanding it through the distributive law. You guys with me? So what is the point here? The point is that each column gives you a P and G, and then you go through an additional sum of products logic expression to get the P's and G's of each group of 3, and then you can generate each carry out of each group as a function of the P's and G's from the groups to its right. You guys with me? So the advantage of this is that the delay is in terms of the number of groups as opposed to the number of bits, which is shown here. N is the number of bits, K is the number of bits per group, N divided K is the number of groups. So the delay is going to scale still with N, but it's going to scale a little bit better because you're dividing N by K. Everyone with me? Okay. And then finally, the prefix adder. Prefix adder is based on this concept that you can calculate G and P from a group of bits by splitting that group of bits into 2. So the range of bits is I to J, and you can split that into inputs I to K and K minus 1 down to J. So I should say I down to K and K minus 1 down to J. Does that make sense? So that's the thing you have to understand in order to get how the prefix adder works, is that you can calculate the generate and the propagate from a range of bits, not just in groups of 4 as we did before. So this just generates these P and G's for every group of 4. But instead, you can generate them based on a group of bits where you treat it like 2 halves, an upper half and a lower half. So why? What's the point of doing this? Well, the point is that you can build, you're taking 2 inputs and creating 1 output, which gives you kind of like a tree node. So then you can use that to build a binary tree where now this diagram is a little confusing, but once you understand it, it's not too bad. What's shown here is that these are the columns up here. So this is a column being a pair of bits from the 2 inputs. Each of those columns is generating a P and a G, just as we had before. So we have a propagate and generate associated with each column. That's not shown in here. Once you've got those, then you have these black lines come out, and these black lines represent the P and the G associated with that group of bits. So in this case, I've got, bit 2, column 2 and column 1's P and G's both come out and they go into this black box. This black box represents this circuit down here. This first circuit is just the white box. The black box is this circuit. That circuit is representing these equations, these expressions. And then you can follow this pattern where you take each output from each black box and combine it with another output from a black box, and you get this binary, like this binary tree, where eventually you'll get 1 output that comes out to an output column that comes from 1 black box. And if you look at the inputs to that black box, in this case it's, like for example, if I take 5, that comes up here, that is the propagate and generate from 4 down to -1, which itself is comprised from 4 down to 3 and 2 down to -1. So you have all these different pairings of ranges that come together that give you the final output. And then once you've got all those, then you've got the carry in to each output bit. Once you've got the carry in, then it's just a matter of sticking that along with the 2 inputs into an XOR gate. Okay, so the advantage of this is that its delay scales with the log base 2 of the number of bits. So all of these adders get slower as you add bits. This is a question of how slower do they, how do they scale, right? How much slower do they get as you increase n? In this case, as I increase n, the number of input bits, the delay scales up as the log base 2, right? So you've got the log base 2n times this TPG prefix, which is the delay of those black boxes, right? So what that means is that this is a 16-bit adder. The log base 2 of 16 is 4, which makes sense. I got to go through 1, 2, 3, 4. 4 layers of those black boxes. So like I said, each one of these output bits, if you trace it up, it creates a binary tree, right? Okay. And then, of course, TPG is just the initial PG that comes out of these white boxes, which is this circuit, which is only 1 gate delay, right? So TPG is 1 gate delay. You expect that to be a smaller number than the black box delay here, because in this case you got to go through 2 gates, right? And then the XOR is this. You have to add the XOR because that's how you calculate the final sum. Once you have all of the generates coming into each output bit, you have to feed those through this 3-input XOR to get the sum. Make sense? So if you look at this picture and you compare it to the equation, this picture, these 3 circuits match up to these 3 terms in the delay equation. Okay, any questions? Okay, all right, so then we talked about once you have an adder, you can package it into a symbol, like a module, a block, we can go up one layer in the design hierarchy, and we've got this adder. And from an adder, we can create a subtractor by bolting some stuff around it. Specifically, if we take B and invert B and then set the carry in to 1, that effectively negates B because it does a 2's complement, right? We invert all the bits of B and then add a 1. Okay, so we got a subtractor. Then this kind of jumps to this other operation, equality. If we want to check instead of doing an arithmetic operation, if we want to be able to compare two values, multi-bit values, you can compare them for equality by doing an XOR between each pair of bits in the two inputs, and then fanning all those in, XNOR rather, XNOR you fan those all into an AND gate. Everyone see that? So this will give you a 1 if all of the bits of A and B are equal, if they all match up. If they all match up, the XNOR will give you a 1. So an XOR will give you 1 if you feed it a 0, 0, or a 1, 1. Make sense? Now, it's kind of interesting. The other approach here, just as a side note, you could also subtract the two numbers and check to see if the result is 0. The problem with that, though, is that if you subtract A and B, then how do you tell if the result is 0? You'd have to feed it through this, right? But possibly not. I think there's probably a more efficient way to do it if you know that B is a constant, right? In this case, this circuit allows A and B to both be given as inputs. Anyway. Okay, and then A less than B. Now, by the way, you might have noticed that we've talked about add, subtract, equal, comparison for equal, and in this case, comparison for less than. We're actually, if you remember from 212, we're walking through all of the classic MIPS operations. So eventually we're going to take these and combine them into an ALU that we'll use in a CPU design. Okay, so less than is A, you subtract A minus B, and you just check the sign of the output. So if you subtract B from A and the result is negative, that means that A must have been less than B. Is that right? Yeah. Does that work for sign numbers too? Like let's say A is negative, B is positive. Let's figure that out, right? What if A is negative? Well, if it's 2's complement, right? So if A is negative, and B is positive, I already know that A is less than B, right? It is by definition because it's negative, right? But this circuit doesn't necessarily look at that. It's going to take A and subtract B, and so I'm going to have a positive number. Negative number. I'm going to subtract a positive number from that, right? So that's going to give me a negative number, right? So that works. What if A is negative and B is negative? If I take A, which is negative, and I subtract B, which is negative, I'll be essentially adding the absolute value of B, right? And if the result is still negative, then A must have been a more negative number than B in the first place, meaning that it was less than B. So that works, right? Right? Okay. What happens if they're both negative, though, and A is greater than B or equal to B? Well, if let's see, if they're both negative and they're equal, then like negative 10 minus negative 10 is going to give me 0, in which case the sign bit is 0, which means that A is not less than B, so that works out. And if A and B, let's say A is negative 10 and B is negative 9, say A is negative 9 and B is negative 10, and I'll subtract, I'll end up with a positive number, in which case it still works out. So yeah, that's good. It works. Make sense? All right. So let's say we create an ALU, we give it A and B, it produces Y, but instead of having this thing just always add or always subtract or always compare, we'll give it this F, which is a function code, which is 3 bits, and it tells the ALU what operation to do on A and B. So it's kind of like makes it into like a calculator. If F is, there's 8 possible values of F, that gives us 8 possible operation codes. The ones that the book's got set up here is bitwise AND, bitwise OR, add, and then it's got bitwise AND, bitwise OR, and subtract, but for these bitwise AND and bitwise OR, it's negating B. You guys see that? Right? And then set less than. And then there's one code that's not used, which is okay. So we got seven different things this ALU can do. The question is, you look at this and you're like, well, why? I mean, why those code words? Why is it set up this way? Well, it doesn't have to be. This is a design that the book authors put in, and they designed it to try to make it as simple as possible. They tried to make it as efficient as possible. The way they did it was they put one adder in, right? So you notice that there's an add and a subtract, right? And a set less than. And all 3 of those things share one adder. So we have 3 possible operations, but only one physical adder. Now, how does that work? How do they do that? They have a mux up here that is put right before the second input on the adder that allows you to toggle between the second input on the adder getting B straight out or a complemented form of B. So that's controlled by the most significant bit of the function code, F2. Right? So that makes sense. If you look at whenever F2 is 1, that would be the bottom half of this table. Notice that B is negated, B is negated. There's a subtract, which involves negating B. And an SLT, which does a subtract, which also involves negating B. I should say complementing B. You guys with me? Okay, so that makes sense. And then there's a big mux down here that is a 4-to-1 mux, and it takes the right 2 bits of F. So if the bits 1 down to 0, which is the rightmost 2 bits, 0, 0, it's the output of the AND gate. If it's 0, 1, it's the output of the NOR gate. Well, you can see that between this guy selecting the AND or the OR and this F2 selecting whether I negate B, that's how I get these 2 operations, the AND, the OR, and the other AND and OR that negates B. Make sense? So I get these 4 out of the 7 operations are implemented just by these two muxes and the 2 gates here, right? Now, one of the things that used to surprise me when I first started learning about this stuff was, notice how it does an AND and an OR and an add all the time. Regardless of what I tell this ALU to do, it calculates results redundantly, right? It calculates these AND and OR and sum, even if I'm not doing anything that relates to a sum. Make sense? Like if I could be doing a bitwise AND, but yet it's still going to be, this adder is still going, it's still operating, right? And it's generating a result, it's just not being used for anything because it gets stopped down here at this mux. It doesn't get routed through the mux. I used to think, geez, that's wasteful, right? But that's how things worked for a long time until about 10 years ago, and then chips started, incorporating these power-saving features that could potentially, power down this adder when it's not being used. Everyone with me? Okay. But by the way, the idea of calculating all of these potential results and only using one is really, the essence of concurrent semantics. You do everything and then You do everything at the same. You do all possible operations, and then you select one at the end with the mux. Right? Okay. Let's see. The subtract is implemented by negating b, and then also taking this f2, the first bit of the function code, and connecting it not only to this mux, but also to that carry-in input. Carry-in on the adder, which performs the 2's complement of b, creates the subtract operation, or it implements the subtract operation. You guys with me? This is called a fan out. This is when I have one input that's connected to two things in the design. It's fanned out. And then lastly, notice that for the set less than operation, it's 1, 1, 1, which means the first 1 sets this to 1, so negates b and adds 1 over here in the adder as a carry-in. Then the second 1, 1 selects this input on the mux, and this input has this block here called 0 extend, which is taking bit n-1 from the output of the adder, which is the sign bit. It's just essentially a flag saying whether the difference is a negative number. And then it 0 extends it, meaning that I have to produce a 32-bit result here for y, but the sign bit is only 1 bit. So I have to convert 1 bit to 32 bits, and that's done through this 0 extend. You guys with me? MIPS is the only processor I know of that does this, by the way. Any other processor, RISC, RISC-V, ARM, Intel, IBM 360, forget how, just about every other processor does not put 31 zeros and a bit to represent whether an input is less than another. Generally, the way that works is when you compare two numbers, the result, the flag that indicates whether the comparison is true or false, goes into a flags register, as opposed to being generated as a 32-bit result that wastes 31 bits. You guys with me? Now, why do you suppose MIPS does it that way? Well, it turns out that that was done deliberately because the flags register, if you calculate something that modifies the flags register and then you subsequently use the flags register for a future operation, like a branch condition, that creates a data hazard, which you guys hopefully learned about in 212. So the MIPS guys were hoping to avoid data hazards involving a flags register, because that complicates pipelining. If you're pipelining, if you have a pipeline processor and you have potential data hazards with a flags register, then you would have to pass the whole flags register down the pipeline and maintain different copies of the flag register at different locations in the pipeline, which was a pretty bad. Hennessy and Patterson didn't like that. They thought that that was bad form. So instead, they treated the condition codes of a comparison as if they were just a regular calculated number. So that's why you have this 0 extend. Does that make sense? That's a little bit of history behind this. But basically, the 0 extend just plops in, whenever you do a comparison, whenever you do this SLT, it plops in 31 0 bits, followed by the bit that actually denotes whether A is less than B. You guys with me? Okay. So this is an example. If I want to know if A is less than B, then this is the 0 extending I was just talking about. So if A is 25 and B is 32, we do an SLT operation. We expect the output to be a true because 25 is less than 32, but true and false only requires 1 bit, and we have 32 bits output. So you'll see that there's all these leading 0 bits that are packed in here because of the 0 extending. But to do that, we'd have to set the function code to 111. That's based on the table, but also on the design. The first one is tells the adder to act as a subtractor, and the second 11 selects the third input on that mux. You guys with me? So internally, if I were to look at this, if I were simulating this in model sim, I could put those two inputs there, and then I could grab this signal, S, right? Because it's an internal signal. Whenever you simulate in model sim, or any other behavioral simulator, you can grab values that are not inputs and outputs. You can go in and look at internal values like this S. And S should be showing 25, whatever the difference, 25 minus 32, right? So it's going to be -7, right? So S is -7, but that -7 never sees the light of day here. It gets kind of trapped in there because this multiplexer doesn't route the -7 through to the Y. All it does is it grabs the negative, the 1 bit from the -7, and as 0 extends it, and it routes that one out instead, right? So even though this adder is giving us -7, the only way you'd see that is if you had a simulation tool that you could go in and you could inspect, you could drill down and inspect that internal signal. Okay, so how about shifting? Shifting is one of those things that I know in 212, when I taught 212, no one had ever heard of shifting. So I spent all this time lecturing on shifting and shifters, and everyone was like, why? We never did shifting in 145, 146, 240, 274. When do you use shifting? What is that for? Right? Everyone always looked at me like I was crazy spending so much time on shifters. But shifting is used a lot. I don't know how much you've used it even at this point, but shifting is used anytime you have to manipulate bits. When you have to look at bit fields, like if you have certain bits that you want to pull out of a number, you generally do it with shifting. Shifting is used quite a bit whenever you do lower level programming. You may not do it in 145, 146, or 240, but if you ever do any kind of embedded programming, there's a good chance that you'll need shifts, right? So what is shifting? Well, this is always something that's kind of hard to explain. I still don't know how to explain it. Shifting is when you take the bits, and you pretend as though they're like on a tape, and then you take that tape and you kind of pull it to one side or the other. What really happens if I shift to the right, in this case, I have this value 11001, and I'm assuming, by the way, that I have a 5-bit register. I don't know why they use 5 bits. That's kind of a strange number, but let's pretend we have a 5-bit register and I want to shift it 2 bits to the right. It means that 2 bits are going to be lost forever, right? The rightmost 2 bits are just eliminated. They're shifted off the end. And that creates kind of like a vacuum on the left-hand side. You have to shift bits in if you shift bits out. So a logical shifter always shifts 2 bits in, right? So in this case, if I have 11001, that 01 on the right-hand side is lost. And it will add a 00 to the left-hand side. The important thing about shifting is that it reassociates the bits inside a register with their positions, right? So every position in a register has a significance, right? There's the rightmost bit is the least significant, the leftmost bit is, the most significant, but also could be treated as a sign bit. Every bit has a purpose in its position. And so when you shift, you change that. And that's really what, you're doing shifting for. So what's happening there is I destroy these 2 bits on the right, and this bit over here, number 1, that used to be the most significant, is no longer going to be the most significant. It is now going to be the 3rd to the most significant, because it's going to get shifted to the left towards the lesser significance bits. You guys with me? All right? Okay. So anyway, left shift is the opposite. You knock off the bits on the left-hand side and you shift in bits, zeros to the right-hand side. So arithmetic shift is when it's the same thing, except whenever you do a right shift, instead of shifting in zeros all the time, you only shift in zeros if the original sign bit was 0. You guys make sense, right? So the idea is that you don't want to change the sign bit by having shifted it to the right. Sometimes, like in Verilog and in some architectures, you'll have an arithmetic left shift. Actually, even C and Java have it too, if you use or maybe it's just, now I forget, is it just Verilog? but I might just be Verilog, sorry. If you have 3 less than, that's an arithmetic left shift in Verilog. I don't know if that works in C and Java, right? Now, you might be saying, wait a second, how does it make sense to do an arithmetic left shift? That doesn't make sense, right? You're not shifting into the signed bit position, you're shifting out of the signed bit position, right? Why do you do that? It took me years to figure this out. It turns out the reason for that is if you do a left shift and you shift if you're using something that supports negative shift amounts, then by doing a left shift by negative amount, you actually do a right shift. So that's the reason for that. And then finally, there's the rotate function, which is something that is actually shifting is pretty common, but rotating is not. It's pretty obscure. Some architectures support rotate instructions. I think most of the ones I've used don't. If you want to do rotate, you have to implement it in software by doing 2 shifts and followed by an OR operation. But basically, a rotate is a shift, but instead of shifting zeros in, you shift in the bits that you shifted out. So you rotate the bits left or right. I don't think I've ever actually needed to do a rotate operation. I used to, in my 212 course, I used to have a test question where I'd say implement a rotate using, in assembly language. Right, so the way you do that is if I told you to rotate, in MIPS doesn't have a rotate instruction. So if I told you to rotate n bits to the right, the way you do it is you would first actually shift to the left by 32 minus n. Right? And then you'd save that as an intermediate value, and then you would shift by n bits to the right, and then you'd OR the values together. So basically, the left shift at the beginning saves the bits that you will be shifting off when you do the right shift. Right? That's a rotate. Any questions about that? Okay. So a lot of times you'll hear people talk about barrel shifters. Like, for example, in my 313 course, we have a processor that we can create on an FPGA. And when you create that processor, the tools will ask you, do you want a barrel shifter? And it's like, why do we care? Like, why are you asking? Why is this important? Well, barrel shifters obviously give you the ability to shift as a hardware instruction, right? As opposed to having to do it with, write a little program that does the shift with a loop, right? But why do we care? Why is that a question? Well, it turns out barrel shifters are expensive in hardware. It costs you a lot in terms of hardware resources to make a shifter. Why? Well, because they look like this. This circuit shows one multiplexer for every output of the shifter. And then each of those multiplexers have one input for all of the inputs. Right? So think about it. Now, this is a 4-bit. If this was 32-bit, I would have to have 32-bit, 32 multiplexers, and each multiplexers would have to be 32 inputs. That would create a full 32 by 32, what's called a crossbar switch. Basically allows you to connect any input to any output. Those scale up as a factor of n squared. Right? Remember the adders that we talked about, the prefix adder scales up as a function of log n. This scales up as n squared. So this is much more expensive than an adder, even a ripple carry adder. Well, I'm comparing resources to latency, but yeah, but it also equates to hardware, right? Well, anyway, you get the idea, right? You need a lot of these. Why? Well, the idea is that you take these inputs, and you have to be able to figure out how much you want to shift, and for each shift position, you have to set these multiplexers to a different value. So, for example, if I want to shift by 2, say, right, this thing allows me to say, okay, this is a 4 bits, and the shift amount is 2 bits, right? So I can shift by 0, 1, 2, or 3, right? And so, obviously, I can only shift one way here. So which way am I shifting? Well, A3, let's see, if this guy is set to 2, then I'm going to take input 2 and notice that is a 0, right? So the most significant bit will be a 0, right? The bit 2 will be, let's see, what is that going to be? Oh, sorry, this is 2, right. 2. 2 will be also a 0, right? So what does that mean? It means bit 3 and bit 2 are both going to be zeros, meaning that this is a right shift. This circuit is showing a right shift operation because by setting the multiplexers to 2, each multiplexer select is the shift amount. This shift amount is fanned out to all the multiplexers select. So if I tell it to shift by 2, I'm going to get 2 zeros are going to come in the left-hand side, the most significant the bits of the output, the Y3 and Y2. Y1, on the other hand, is going to be what? Y1 is going to be, again, input 2. Where does that go? Bit 3? That makes sense. So that means the most significant bit of A, after I shift it, is now the second to the least significant bit of the output, right? Because I shifted it down 2 positions, right, to the right. So I took bit 3 and made it bit 1. 3 minus 2 is 1, right? And then finally, this last guy is going to be A2 is going to go out and become Y2, which again makes sense. 2 minus 2 is 0, and then A1 and A0 are not going anywhere. They're just they're not being routed out of any of the muxes, meaning they're being shifted off. You guys with me? Okay. Okay, so another uses of shifters, you could use them they're used when you do multiply and divide, both in hardware and in software. So one of the other projects I had in 212 was I would have everyone write a multiplier and a divider in assembly code using only shifts and adds and subtracts, right? And the reason for that is because if you shift to the left by n bits, you're actually multiplying the value by 2 to the nth power. So if I shift by 3 bits to the left, I'm multiplying by 8. If I shift 4 bits to the left, I'm multiplying by 16. Likewise, shifting to the right is like dividing by 2 to the n power. So if I shift 2 bits to the right, I'm dividing by 4. 2 bits to the right, dividing by 4, right? But if I'm doing shifting for the purpose of dividing, then you want to make sure that you use a arithmetic shift, because if you might not think of this, but if you have a negative number, you can divide it using the shift method, right? So let's say I have negative 11. Let's say negative 11. What is that? 11 is 8 and 3. Looks like that, right? And I'll give it a leading 0 there. So I'll make it a 5-bit number, right? And 2's complement, that would be, I'd have to invert 1, 0, 1, 0, 0, and then add 1. 1, 0, 1, 0, 1. All right, so this is negative 11. Now let's say I want to divide that by 4. So I will shift it to the right by 2 bits, which will eliminate those 2 bits and will add 2 1 bits on the left because the original sign bit was 1, right? So my new number is that. 11101. What is that? Well, what do we expect it to be? What's negative 11 divided by 4? Anyone know? Yeah, negative 2.75. But remember, we can't do fractions, right? These are integers. So the 0.75 would get, truncated. So what would the result be? Yeah, that's right. It would be negative 3 because you would round that down, right? If you round negative 2.75 down, you get to negative 3. So is that equal to negative 3? Well, I don't know. I can't do that in my head. I have to take the 2's complement of this to figure it out. So the 2's complement of this, I have to complement each number, 0, 0, 0, 1, 0, and then add 1. 0, 0, 0, 1, 1, and look at that, it's 3. So it worked, right? But that's why you need to make sure that you do an arithmetic shift, because had I done a logical shift, it would have put zeros in here, and that would have guaranteed that the result would have been a positive number, which means, wouldn't have been right. Okay, how about multiplying? How do you multiply by a number that's not a power of 2 with a shifter? Right? What if I don't want to multiply by 2, 4, 8, 16, 32, 64? How do I do that? Well, it's actually, if you take the number that you want to multiply by and you break it up, you convert it to binary. So let's say I want to multiply by 3. This is another question I used to ask in 211. Write code, write the shortest possible snippet of MIPS code that multiplies a number by 3 without using a multiply instruction. Well, you can take the number and multiply it by 2 by shifting 1 bit to the left, right? Right? Then I just take the original value and add it to that. Right? So I have the number multiplied by 2, and then add that number again, it becomes multiplied by 3, right? It's like saying, take a number like, say, 11. Take 11, you shift it to the right, shift it to the left by 1 bit, that gives you 22. And then add 11 to that. That gets you to 33, right? Well, how does that work? Well, basically, you just take 11 is your multiplicand, which is a weird word, multiplicand, and you want to multiply it by 3. That 3 is your multiplier, right? So you want to take the multiplier, look at it as a binary number. So, 3 would just be like, say, 1, 0, 0, 1, 1. Say, make it a 4-bit number. 0, 0, 1, 1. And then each of those bits in the multiplier represents the amount I want to shift the multiplicand by and accumulate. Meaning, that's bit 0 and that's bit 1. So I want to shift it by 1 bit and shift it by 0 bits. Add them all up. You guys with me? Let's say I want to multiply by, say, 11. 8, 1, 0, 1, 1. 11. Again, I want to say 11 times 11. So I have 11. I want to multiply it by 11. So I look at the multiplier 11, 1, 0, 1, 1, and I've got bit 3, bit 1, and bit 0 set in there, right? It's 1, right? So I take 11 and I shift it by 3, which is going to give me 11 times 2 to the third. And I'm going to add, shift it by 1, 11 times 2 to the first. And then 0, I'm going to add 11 times 2 to the 0th. Right? So I add all those up. That gives me 88. That gives me 22. And that gives me 11. 88 plus 22 plus 11 should be, 121? 121. 121. 11 times 11. Make sense? So multiplying is pretty easy, right? It's just, you just look at the multiplier and you use it as a guideline to how many times you have to shift. Now the problem though is that hardware-wise, the complication there is that you have to be able to add for every bit in the multiplier, right? So if I'm doing a 32-bit multiplier, I got to have 32 adders, right? Well, I have to do 32 add operations. I may not need 32 physical adders. I got to add 32 times. That kind of stinks, right? How do I get around that? What do I do about that? That means that, so that basically means that multiplying is n times more expensive than adding, where n is the bit width. That's a lot. Yeah, well, that's what this is. This is how you do it in hardware, except check out, this is kind of slick how they do it here. They've got all these adders, right? But these are all 1-bit adders. Right? So you've got, they break it down by bit, right? So the idea is that if I've got A and B, in this case they're 4-bit numbers, I could take A bit 0 and B bit 0 and add them. And that automatically gives me the least significant bit of the result right there. I'm done. That's the rightmost bit of the product, right? Now, I'm only going to do that, by the way, if the least significant bit of the multiplier is 1. So the way they get around that is they put in this, well, in this case, they don't even need an adder. It's literally just, it's an AND gate, right? So if these two inputs are both 1, the product is 1, right? Now, when you move to the next one, I've got A bit 1 and B bit 1. Okay, so those ones I have to add together A1 and B0 and A0 and B1. You see that? Makes sense, right? So there you just take the two A bit 1, B bit 0 and AND them, which is done here, and A bit 0, B bit 1, and AND those, and you feed those into an adder, a 1-bit adder, full adder. Make sense? Okay. Next, the next column is I got to add 3 bits together. And so you'll see that in this case I've got 3 adders that are connected in series. That makes sense? Now this is still growing pretty fast though, because you can see that as I get further to the left here, I have more adders in series. But this is, I don't remember what this type of multiplier. There's different ways. There's many different adder or multiplier architectures. This is one type. Everyone see how that works? Essentially, you're just using full adders to implement sort of elementary school style multiplication, bit by bit. Okay, the divider I'm going to skip because this is really confusing. Basically, the idea, I'm not going to spend a lot of time on it, but the idea is that the divider is, the way that you do dividing is, again, similar to the way you do it in grade school. The problem is that a divider has conditional behavior in it. Because you have to figure out, so like if you have a number, like say I have 789, and I don't want to divide it by 9, 2, 3, 1, 2, 5. Say I do a divide like that. Now, as a human being, you know right off the get-go, just by looking at this, that what do? I take the 789 and I subtract it from 923. Why? Because the reason I do that is because and I put a 1 here, right? Is that right? Yeah. Right. So I put a 1 here, and then I subtract these 3 digits, my divider, from the first 3 digits of my dividend. You guys with me? I do that just, I can see it, right? That's how you're trained to do this. But the hardware can't do that. The hardware has to basically try first to take the 789 and line it up like this, which is wrong. But what happens is if I have 9 and I subtract 789, I get a negative number, right? So the divider then, in response to that, it will put a 0 up here in the quotient as the first bit of the quotient, and then it will shift the 789 down 1 position, is such that I have to now subtract 789 from 92. That also results in a negative number, so I stick a 0 up here in my quotient and I move that over again. And now I'm pretty much at where I would start if I was a human being doing this. I subtract 789 from 923. I can do that. That gives me a positive number, or 0. I should say non-negative number. So I put a 1 up there, and now I actually subtract these guys. So this is 4, and this is 34, right? 134. Right? And then I have to bring down the 1. And now I have to figure out what number I put in here to multiply by that to subtract from that, right? The divider in hardware has to do the same thing. It has to it takes the divisor and it tries to subtract it. It takes the divisor and shifts it to the left. Tries to subtract it from this dividend. And if you get a negative number, it keeps shifting it to the right until it successfully is able to do a subtraction, at which point it sets the remainder register to that and continues the process. So you have this conditional logic in there that tries to subtract, checks the sign of the difference, and then either adds the number back or keeps the number in there and puts a 1 or a 0 into the quotient as a result. And so you end up having to, this array, they have an array architecture to do that, but I mean, and this is the algorithm. This algorithm describes what I just did there, except in binary. But the problem is it's confusing to try to trace this through. It's tough. It's also the reason why, these are expensive and slow. It's the reason why a lot of processors don't even have a hardware divide. It's very rare. ARM does not, I believe. ARM v7. ARM v8 might. I forget. I used to know this stuff. A lot of architectures don't do divide in hardware. By the way, in the original version of this course, we were doing this ALU on an FPGA, and I thought, well, Verilog has a divide operation, right? So I'll just write a Verilog module, I'll tell it to divide, and I'll synthesize it, and voila, I'll have a divider. Simple. I'll let the synthesizer decide how to generate a divider. Well, it didn't work out so well. It used the whole chip. The whole FPGA got eaten up just for the divide. So you can't do that. You can't just say divide in Verilog and synthesize it. That's a disaster too. Okay. So dividers are slow and they use a lot of hardware. Is my point there. Okay. So the next topic in the book is actually something I covered back in chapter 1. I jumped the gun a little bit. I was a little too excited about this. I didn't want to wait. Fixed point numbers. So hopefully you guys remember fixed point numbers. Fixed point is a way to do fractional numbers without floating point. You guys are all familiar with floating point, but you don't need floating point to do fractional. Floating point is not the same as fractional. Floating point means fractional with a huge dynamic range. But if you don't need a huge range, then you can use fixed point, which is where you just imagine that there's a decimal point, although it's, decimal is implies base 10, so you should call it radix point. But you put a point in there, and then some of the bits, it just changes the significance of the bits. So we already talked about this. I'm going to just scroll through this. You guys all remember fixed point? Okay, then there's floating point, and this is probably also review for you from 212. floating point is kind of like fixed point, except the decimal point, the radix point, can float. Specifically, it floats if you have a number like 1. So the problem with fixed point, by the way, is that if I have a fixed point number like this, right? This is 3 in decimal. This would be 3 point. What is that number? That's 5/8. 3 and 5/8. 11.101. I know it's 5/8 because that's 5, and there's 3 bits to the right of the decimal point, so each one is an eighth, right? 3/8. 5/8. Sorry, 5/8. Make sense? The problem is that what happens if this? I mean, this makes sense, but what happens if this number is, I've only got, 5 bits here, right? What if it's an 8-bit number? What if it's an 8-bit register, I should say? Well, that means I got to put 3 leading zeros here. Right? And the problem is that these 3 leading zeros do not contribute to the precision of the number, meaning that I wasted them. Leading zeros don't help me. Right? So they hurt they reduce your precision, because this number is effectively a 5 bits of precision, even though this is I've got 8-bit register to put it in. You guys with me? I don't know if you guys ever noticed this. In digital photography, it's kind of cool where, cameras use fixed point, right? So the camera sensor has a red, green, and a blue component, but they're all 8 bits. So you have 8 bits of red, 8 bits of green, 8 bits of blue, which is fine, except if you're taking a picture of a dark room, then your red, green, and blue are low values. And thus, all of the bits, those 8 bits that you store red, green, and blue, all of the leading zeros are wasted. And so what happens, you bring it into Photoshop or you bring it in Lightroom and you say, I'm going to boost this up. I'm going to boost up the gain. I want to get this thing brighter. It was too dark. You boost it up, all of a sudden everything's pixelated. And you're like, why is this thing pixelated? This is a $6,000 camera. I got a pixelated picture here. What's going on? Well, it turns out that when you boosted those numbers, you multiplied essentially, if you only used, if the picture was so dark that you only used the low order 3 bits of the red, green, and blue channel, you basically just had 3 bits of precision. You had 3 bits of color resolution. And so you ended up with a crappy picture when you boost it up, when you brighten it up. So kind of the same idea with fixed point. You get these leading zeros are kind of wasted, right? So floating point fixes that by basically it allows you to move the decimal point. So I don't have to lock it in here where I just have always 3 fractional bits. I could say, oh, you don't need those bits? Well, we're going to use scientific notation, and I'm going to give you those bits over here on the right-hand side. Make them fractional bits. You can use them now. So that way, with a floating point number, I always get the precision is always the number of bits I have in the number, whatever my significant size is. You guys with me? So you guys have single precision and double precision represents the number of bits of precision I have, which I always get no matter what the value of the number is. You guys with me? And then, of course, the other advantage is that by being able to move that decimal point around, I get a massive range. I could represent really small numbers and numbers that are really teeny tiny and numbers that are really big, because I can move the decimal point to whatever. I can make the bits as significant as I want. I can give these bits as much value as I want, and I get all my bits of precision. You guys with me? Okay. So how does it do that? Basically, it's a packed data type. You've got a mantissa, a base, and an exponent field. Mantissa is the number. The base is, the base is not stored actually. The base is always 2 because it's binary. The exponent is the exponent. So, for example, if I want this number, what is this number? This is 3 and 5/8. It would be 3 and 5/8, like that, right? I would store this in scientific notation, meaning that I would always put this decimal point after the first one. And then I would adjust I would tell the user that by setting the exponent to however many positions I move the decimal point. So in this case, I had to move it one position to the left, so my exponent is 1. And so thus, my number is no longer 3 5/8. My number is 1 and, what is that? 1101, 8 plus 5 is 13/16 times 2 to the first power, which is also equal to 3 5/8. That lets me use all of the bits in my significant. The other thing too is that because in scientific notation I always have a leading 1 bit there, so I don't have to actually store that. I can just imply it. I can just assume that there's always a 1 point something. So all I have to store is actually this part of the number, the fractional part. That's with me? So what that means is that the significand, in a single precision number, the significand is 23? Is it 23? 23. 23 bits. 23 bits. Not including the leading 1 bit. So physically, this mantissa is representing a number that is this value times 2 to the negative 23rd power. Plus 1. Plus 1 because there's a leading 1 bit. You guys with me? Make sense? So think of this as a fixed point number where all the bits are fractional. So if I have 23 bits, the value stored in here is the value divided by 2 to the 23rd power, which is 8 million. Roughly 8 million. So these are 8 millionths, right? Then I take that value and I multiply it by 2 raised to the power of whatever is in the exponent. That way I can adjust the decimal point. So what does that mean exactly? Well, the exponent, first of all, is a signed number. So 8 bits, what's the range there? Well, in 2's complement, it would be negative, it is an unsigned, it would be 0 to 255, right? As a 2's complement, it would be negative 128 to positive 127, right? And right? But actually, they do this weird thing where they use bias notation, so they adjust it. They don't use 2's complement. So the range is actually negative 127 to positive 128. You guys with me? So what does that mean? That means that if this number is, if the exponent is negative, what does that mean? It means it's a value that's between 0 and 1, right? So all of these numbers from negative 127 all the way to negative 1 all represent numbers that are between 0 and 1, right? Which means half the dang values that you can represent in floating point are between 0 and 1. Well, actually, negative 1 and 1. You guys with me? Is that weird? I mean, think about that, right? If you look at the number line here, 0, negative 1, positive 1. Half of all the floating point numbers are in this range. Half of all the numbers I can represent are in this range, negative 1 to positive 1. The other half is everything outside that range, right? Pretty crazy, huh? Okay, anyway, you guys remember all this stuff, right? The floating point stuff? Okay, gotcha. Okay. Okay, I'll just run through this real quick then. Converting a number to binary. In this case, 228 is that. You convert it to scientific notation, which means that you put a dot after the leading 1 bit. Then you count the number of positions you had to move it, which in this case was 7. So that's a scientific notation. And then the sign bit of the mantissa is 0. The exponent is 7. And the significant is everything here. 1, 1, 0, 0, 1, 1, 1. Wait, what? Oh, sorry. 1, 1, 0. Yeah, 1, 1. How the heck did I get that? 1, 1. Oh, they're including the leading 1 bit, I guess. Okay, yeah. So they got the leading 1 bit here. So they're going to have to take this off, right? And then the exponent, they're just showing as 7. They haven't biased this yet. So you have to add 127 to this. So this should be 130 in the exponent field. And this mantissa field should not have that leading 1, right? Yeah, there you go. They fixed it. And they fixed that. Good. All right. So I will skip over that. Okay. So, let's see. How much? Okay, so we'll skip over. So the problem is, you can still have underflow and overflow. Those are represented by errors, like not a number. So there's codes for that. And there's 4 different rounding modes on floating point. I don't know how to change that. Right? Never figured that out. Like if I'm writing a Java program and I do a floating point add, how do I tell the Java virtual machine that I want to use toward 0 rounding mode as opposed to up rounding mode? Unclear. Never figured that one out. But there are 4 different rounding modes supported. Not unclear which one we're using when we're using Python or C or Java. Okay. Adding floating point numbers is expensive. You should only do it when you really need to. Why? Well, it's simply because you have to compare the exponents, find the one that's smaller, denormalize the smaller one, add them, renormalize, and re-round, and it takes a while. Also, whenever you denormalize one of the numbers, you shift, and what do we talk about in shifting? You shift. Every time you shift, you lose bits, right? And so that creates round-off error. So every single time you do a floating point operation, unless the exponent of the 2 numbers that you're adding match, you're going to lose data off the one that has a smaller exponent. You're going to round it. Every time. You lose data from the smaller number. You're chopping bits off of the smaller number. So, anyway, okay, so we'll move on. All right, so any questions about floating point? I went through that fast because I think you guys are pretty comfortable with that stuff. Okay, got a few minutes left. Let's talk about counters. I think I showed a couple counters in chapter 2. Counters come up a lot. Actually, didn't we do a divide by 3 counter? I think we did. Yeah. Well, actually, we used a state machine to do a divide by 3 counter. That's right. But I talked about how it was really counting, right? It was a state machine that was counting, where the state represented the current count. And so we would draw it as a finite state machine where I had 1 state per count, right? Well, that's not how you build a counter in reality. That's not a good way to build a counter. An easier way to build a counter is to use an adder as your next state function, essentially. Your next state logic, right? So your state register becomes basically just a register, and the next state function becomes an adder. And that way, whatever's in that register, every clock tick, it'll just add 1 to it, and it becomes a counter, right? So why would we do this? Why do we need this? Well, this comes up a lot. Like, for example, if you make a cache, hopefully you guys covered caches in 212. No. So think about a cache controller, right? So if you get a cache miss, what happens? You have to go out to memory and you have to bring a block of data from memory into the cache, right? Well, how is that going to work? How does that that controller is going to have a counter in it that counts up each of the addresses representing each word that goes in that cache block, right? So you need a counter in there to do that. Also, like, for example, DMA controllers, like whenever you want to send data to a monitor, like if you have a frame buffer and you want to attach a monitor, there's a counter that constantly runs and transfers pixels out of the frame buffer to the monitor, right? It's just a counter that constantly counts up. Okay. There's other variations on this too. Like instead of a counter, you can do this thing. You could put registers, and instead of having an adder feed these registers, you can have the registers feed themselves serially as a chain, right? So these are actually, I should say, flip-flop. Flip-flop. Each flip-flop leads into the next one. This creates a shift register where you can load flip-flops. You load them, and then every cycle you shift by 1 bit. Now you might say, wait a second, I thought you said shifters were expensive. Well, keep in mind that this is not a barrel shifter. This is a 1-bit shifter. It shifts 1 bit position at a time. This doesn't allow you to shift by an arbitrary amount. If you want to shift by, say, 7 bits, you have to wait 7 cycles for it to do that. Any questions about that? Make sense? What do you imagine the problem this could be, though? I used to always take this for granted. It's like, oh yeah, just take registers and connect them in series. You create a shift register. Yeah, possibly, but they're just, you can scale this, right? You can just have as many as you need connected. What's that? Yeah, it's that. But also, like from a practical perspective, remember we talked about hold time, setup and hold time. Well, yeah, I mean, this guy has a contamination delay. If you have these connected this way, this guy's contamination delay is going to arrive at this guy before the hold time. Yeah, before the hold time elapses, right? So actually, and I never realized this because when I was in my digital logic class, we used to make these on breadboards. They worked fine. We just used TTL chips and connect them in series and hooked them up to LEDs, and they shifted. And I was like, oh, that's cool. Then when I learned HDL, I would go in and I'd make these on FPGAs. I'd connect these guys in series. You could do it in Verilog, and you just write a Verilog description of this, and bam, synthesize it, and it works. And then, then this semester I was preparing for this class, and I was like, oh, you can't do that because the hold time will be violated. Well, it turns out that the hold time wasn't violated in the TTL chips because those things were so darn slow. I guess it didn't matter, right? And when you do it on an FPGA with Verilog, the tools they must be putting some extra delays in here that you don't know about. So they don't violate the hold time constraint, right? They're putting buffers in here, but you don't know that from a design perspective. You don't know it's doing that, but it must be because they'd be violating the hold constraint otherwise. As long as they don't violate the hold constraint, though, this will create a nice little shift register that'll shift 1 bit per cycle. Okay, sorry, I'm out of time. Thank you. I'll see you on Wednesday.